Hi everyone, my name is Yuankun Fu from VMware. Now I will present my paper, Designing a 3D Parallel Memory-Aware Lattice Boltzmann Algorithm on Manycore System. This work is done during my PhD research at Purdue University with my advisor, Dr. Feng Guangsong. Let's talk about the motivation of this paper. LBM is an evolving approach to solving complex flow problems with high parallel efficiencies in the CFD community. But LBM suffer large data storage costs and highly memory bounded on current architectures. Our prior work merges multiple time steps in 2D space and presents up to 5 times speed up. This paper aims to augment the memory-aware idea in 3D space. Although it seems straightforward to move from 2D to 3D, but it is significantly much more difficult to design an efficient 3D memory-aware LBM algorithm. And we target solving 3 main challenges as geometry changes from 2D to 3D. Firstly, the required data storage increased from n squared to n cubed, and the data dependency of the lattice model becomes more complicated. There exists single copy distribution method can reduce storage by half, but they require following a set of constraints. So can we combine merge multiple time steps and single copy distribution in 3D together? And secondly, if the first combination is possible, but since normal 3D tiling doesn't apply to this combination, how can we further explore spatial locality? And we propose a prism traversal access pattern to resolve this. Thirdly, when we design a 3D parallel LBM, a non-trivial interaction occurs at the boundaries between threads. How to guarantee the thread safety to avoid risk conditions, and also how to reduce synchronization cost in parallel when we compare to wavefront parallelism. Now let's talk about the existing research on efficient LBM algorithms. They mainly focuses on 2 categories. First is to optimize the memory access within one-time steps due to its iterative nature, like single copy distribution methods, but they require follow a set of constraints. And then wavefront parallelism is another category, but their main issue is highly synchronization costs and cannot combine with single copy distribution method and spatial locality. And for the modern parallel LBM software packages can be classified into matrix-based or adjacent list. In this study, we choose the widely used matrix-based data structure and select the state-of-art Palabos library as the baseline LBM algorithms. And the recent LRNLA cone-field LBM uses recursive data storage and recursively upstate lattice cells, but our using a more straightforward direct matrix-based method to access pattern cells. Now let's look at the baseline 3D LBM algorithm. We call it Fuse Swap algorithm because it combines single copy distribution, swap, and single sweep together. But when combining swap with single sweep, we must guarantee that the populations of neighbors involved in the swap are already in a post-collision state. So the workaround solution is that we need to adjust the traversal order of simulation domains with a predefined order of discrete cell velocities. So each cell can stream its post-collision data by swapping values with half of its neighbors. By the red arrows, we define this operation called swap stream. And also another operation is called revert to locally swap its post-collision distribution to opposite directions. And to make the Fuse Swap LBM more efficient, Palabos pre-process and post-process on the boundary cells respectively. Now let's look at how to design the sequential 3D memory-aware LBM. And we use a case to merge 2 time steps on a 4x4x4 cube lattice. And figure A is the initial state. Green cells are boundary cells, blue cells are inner cells. Then we compute the first computations on layer 1 with the arrows showing row by row. Then we compute on the second layer and on the boundaries. Then we ready to compute the next inner cell layer, inner cells. And then after we compute the first computation, we mark it red, and we notice that the the forward left corner cell is ready for the second computation. So then we can immediately compute on that. So that's we can merge multiple time steps here. Then how to optimize the spatial localities? And when we design, so we design this prism traversal method. And we illustrate this idea by a 4x16x16 cuboid box. And the reason why we call the prism traversal is that the traversal route is either a 3D pyramid prism or a parallel piped prism. Figure A to D are the 4 layers of the cuboid from the bottom layer to the top layers, and the cell with the same numbers forms a prism. For example, the cells with number 1 are in layer 1 to 4 forms a prism pyramid shape, prism 1. And if the cuboid is much larger than this demo, we notice that the majority of prisms are parallel piped shaped. The reason why the planar slice of the prism is either triangle or parallelograms is due to the swap stream operation. When we cutting along the YZ X plane, we have a planar slice as shown here. So we observe that a cell, when it ready to swap with its lower right orange neighbor at direction 9. In other words, the orange cell can swap with the upward road. So it means that its neighbor shifts one cell leftward. So similarly, if the cutting along the XY plane, when a cell swaps its data with the upward road, its neighbor will shift one cell forward. So that's the reason why we get prism shapes. Yeah. Now let's see the complete version of the algorithm. We add 2 more features here, merging 2 time steps and the prism traversal, and also 3 helper functions to make the main structure of the algorithm more cleaner. And now to support a Manycore system, we choose OpenMP to design the parallel 3D LBM. And we use the 8x4x4 cuboid as an example. We will partition this cuboid by 2 threads along the x-axis and the end layer of each subdomain in each thread is called intersections. Okay, this figure shows the initial state at time step t. Okay, then in the stage 1, we do a pre-processing on the intersections. Then we start stage 2 is the main computations in each thread subdomain, and it will handle 5 cases. The first case is that each thread will compute the first computation on the first layers, because this one they can do the swap stream because the intersection layers already we pre-processed on that. Then this is a case 2 when we move forward to next layers. Then whenever a left forward corner cell is ready to compute, we compute on that, but it cannot stream because that the underlying layer haven't compute the second stream. So we cannot compute the stream here, but we can compute the second cleat here and also do the revert operation here so that it can support the upward layer, the second stream. Yeah. And then whenever we encounter case 0, which is on the one more layer upward, and we continue. Then on the intersection layer, we use case 3 to handle on that to compute the first stream operations on that, because previously in the pre-processing we haven't do the stream on that. Okay, then the case 4 is also included in the stage 2. Whenever a cell is ready, we'll compute the second computation on that. And then this is a complete version of the parallel algorithm, still 3 stages, and using the Prism traversal and handle 5 cases, and with post-processing follows. And the reason why we designed this is to keep stress safety, and we will immediately say that why we do that. To handle how to efficiently handle stress safety on intersection layers. We use the arrows A to B to indicate data are transferred from layer A to B, or say layer B depends on A. We can see that in the stage 1, layer 5, the swap stream should be delayed after the revert operation on layer 4. That's why we pre-process on layer 4. And then in the stage 2, we notice that the second swap stream depends on the layer 5 cleat and revert operations, because at that time it cannot do the stream operations on the layer 5. And then we leave the layer 5 swap stream operations when it also depends on the layer 4 swap stream operation. And in the pre-processing, we first do this one, then we do the layer 5 second swap stream. Okay, then we quick look at the experiment evaluation. This is a hardware platform we use. Notice that the KNL doesn't have the L3 cache, and we use the 3D lead-driven cavity as our example. This is the 4 algorithm we evaluated. The first 2 are from Palabos, and these 2 are our algorithm. And let's see the sequential results. And we see that on 3 CPUs, the input cubes are from 64 to 869. And for the Prism algorithm, different tiles are tried. And we notice that when only adding Prism traversal on Haswell and Skylake, it has a 70% speed up and 58% speed up. And then if only adding merging 2 time steps, it has this number of steps. And based on the 2-step, and we add Prism traversal, we still have more speed up. So this is separate thing. And the reason why KNL doesn't have speed up is because it doesn't have an L3 cache. The reason why on the large scale the speed up will decrease is that I'm using the Remora to see that this is related to NUMA memory access. More NUMA memory access will slow down the performance. And then let's see the strong scalability. Given n cores, Palabos will partition domain by 3 axes, but our algorithm only partition in x-axis. And that's why we have 2 input for our algorithm. One is using the identical input, and the other is using the equivalent input, so that each thread in our algorithm has the same subdomain as the Palabos subdomain for each thread. And we see that for small scale, we have 89% speed up, and in the large scale, we have 23 speed up. Similar results on the Skylake And on the KNL, we also have 30% speed up from small to large. And then we can take a look at from a global view. So this is a small scale, and this is a middle scale, and then this is a large scale. And the reason why we don't have we have less speed up on the large scale suggests us in our future work to partition our 3D domain along 3 axes to utilize closer memory page alignment on smaller YZ layers. So the contribution of this work, we designed both sequential and parallel 3D memory-aware LBM with 5 features: single copy distribution, loop fusion, swap algorithm, prism traversal, and merging 2-time steps. And we also present a parallelism method to keep the thread safety on the intersection layers to reduce the synchronization cost with only 3 lightweight barriers. And we also present large-scale experiment evaluations on 3 CPUs, and the sequential can up to 19% speed up, and for the parallel version, we have 89% speed up. For the future work, we will extend it to the distributed memories, and also partition on 3 axes, and also we'll apply this idea to more stencil computations. Thanks so much for attending this talk.